All right, so equilibrium expression. So we're looking at K, the capital K, and that sort of stuff. So there's two main, sometimes you'll see a little, like a KEQ below it for equilibrium constant, or you'll see KC for when you're looking at equilibrium constants dealing with concentration, KP dealing with equilibrium constants when you're dealing with pressure. All right, those are the two most common ones. The whole deal, this is probably the most favorite part of equilibrium expressions for you, is the fact you don't need a unit on this number. Okay, you can just write a number now, and no unit, hallelujah, right? So no more minus 1/2 for not having a unit on your number. So you're good to go. All right, don't be as thrilled about it as I am. Okay, the equilibrium constant is the K value. The whole thing right here, that's the expression. So when they're asking you to write the expression, here's our balanced equation, there's the equilibrium expression. K equals that whole value, that whole thing is the equilibrium expression. Not having numbers plugged in it or anything like that. Okay? All right. Okay, so a lot of times you can write it as, concentrations and stuff. We're not going to include pure solids or pure liquids. So, for example, like H2OL or anything that's marked with a solid in the reaction, we ignore it for our equilibrium expression. Okay, we're going to ignore that for our equilibrium expression. Pretty much the deal is the relative amounts of that stuff stays pretty much constant, right? Because, for solids, the mass and volume, the ratio of those two things don't really change. So mathematically, they kind of look at those as a 1 within the expression. And also in terms of like the liquid too, a lot of times you're doing a reaction in an aqueous situation. So there's already tons of water around anyway. So it doesn't matter. The water that you form in the equation is minuscule in comparison to the actual solution that's taking place. Okay? All right, so let's practice writing a couple of equations here. So if we look at our balanced equation, right, we want to put this together. I'm going to write it as a Kp. I'm just going to write it as pressure. So the way we do this, it's always products over reactants. So in this case, we got pressure of NO2 raised to the 4th power times the pressure of H2O raised to the 6th power. Those are just coming from the balanced equation there, the coefficients in the balanced equation. Then we got the pressure of NH3 to the 4th, and then the pressure of O2 to the 7th. Right, so that's our expression. Not plugging in any numbers. Our expression is just that. You could write them as concentration too if you wanted to. It doesn't really matter. Because they're going to give you either concentrations or units of pressure to use in there. Okay. And we'll talk about tomorrow about kind of the way to convert back and forth between an equilibrium constant, calculating concentration, and one calculated using pressure. But ultimately, we can deal with that more tomorrow. All right, so these ones down below here are just looking at the word equation. We got to, write the equation, balance it, and then write the expression. Okay, so we got the decomposition of solid phosphorus pentachloride. So PCl5, and that's solid. Back and forth arrow here. To liquid phosphorus trichloride, so PCl3, and liquid and chlorine gas, Cl2. So if I were to write this, it would be products over reactants, and it looks balanced. So it just would be pressure of chlorine gas. There you go. Or if we were to write the Kc, it's just going to be the concentration of the chlorine gas, just like that. Either way, it's good right now. All right, and then the second one here, copper 2 sulfate pentahydrate. So copper 2 sulfate, sulfate's got -2 pentahydrates. There's 5 waters, and that's solid. Going to water vapor, and that's gas, and they form copper, solid copper sulfate. Okay, so very similar here. Kp is going to be equal to pressure water to the fifth, or if it was Kc, concentration of the H2O power. Okay, the way it works. Okay, so when they're just asking you for the expression, this is all you have to do. You don't have to plug any numbers in or anything like that. Just give products over reactants. Make sure you're using exponents for the balance equation and stuff, and you're good to go. Okay. All right, because we essentially when we start calculating numbers here, like down below, this lets us know the equilibrium constant is going to tell us whether or not products are favored or reactants are favored. Okay, so because our equilibrium expression is always going to be products over reactants, right? If K is greater than 1, right? If K is greater than 1, what's favored at equilibrium? What? The products, right? Because if it's greater than 1, right, there's got to be more products than reactants. Okay? So that means products favored if it's greater than 1. Okay, if K is less than 1, the reactants are favored. All right, at equilibrium. So that's really all it boils down to. That's what it's telling us. Okay? Some reactions that seem to produce only products have a large K value a lot of times. Some reactions that don't look like they're doing much of anything have a very small. Okay. Okay, so the next reaction here is a very famous reaction, the Haber process here, forming ammonia. Developed in Germany during the World Wars here, when they needed to make more ammonia to make more explosives and dynamite and all that sort of stuff. Yeah, okay. And this guy Haber developed this process. So it is super famous, and it's the main process that we use to make we make ammonia here to put in fertilizer and stuff like that now. Okay, it's hugely important for agriculture and things like that. So yeah, used for bad stuff, and now it's put to use in a good way. Okay, so yeah, you can see there's I can guarantee you in basically every chemistry textbook in the equilibrium section or somewhere in the book that will have the Haber process in there. There'll be a little like bump out section, will describe what goes on with the Haber process, all that sort of thing. It's super famous. Okay, in any event, we got to write the K value. They want us to calculate the K value for this reaction. So first thing we got to do is let's write the equilibrium expression. Okay, so K is going to be equal to the concentration of NH3 squared divided by the concentration of N2 times concentration of H2 cubed. All right, and they give us the values here for ammonium and nitrogen and hydrogen. So we just plug them in. Square that. 7 minus 1 and 3.1 times 7 minus 3. That's cubed. So if we do this, I ended up getting 3,800. Pretty big number, right? Okay, very much product favored. 3,800. No units on that number? Okay, what's up? For 38,000, thank you. Yeah. No, that's what I had. Yeah, that's what I got. 38,000. Okay. Now, if we do the next one here, notice what happened in the reaction. You want us to calculate the equilibrium value of the reverse reaction, right? Okay. So we're able to manipulate K up here, okay, by doing different things. We can manipulate the K value. So we are calculating K. In this instance, we can do, I'm going to call this K prime. We can do this, and it's still going to be prime reactants, right? N2 H2 over ammonia squared. I can do that, plug in the numbers, and go ahead and do that. But a shorter, quicker way is, because we already have the value, we can just recognize that, hey, that's the inverse of our equilibrium constant already, right? So just 1 divided by K. Right? It's the inverse of what we were just doing. Okay. So I got 1 over 38,000. So I got 2.6 times 10 to the minus 5. Okay, so if we reverse the reaction, you can just 1 divided by, okay, the old K value. Down here for the next one, they went through and same reaction, just divided it all by 2, right? Okay, so this one here, I'm going to call this K double prime. This is just K to the 1/2 power because they divided it through by 2. So if they divide or multiply the reaction, we just take the original K value and raise it to that power. Okay? All right. So we can take 3,800, or 38,000, I'm sorry, raise it to the half power. And I got 194. Let me get 195. 194. Okay. Now this is fine and stuff, and this saved us a little bit of work and stuff, but really where it's going to help us out is the next problem. So on the next page, this is really where it makes more of a difference for us. Okay, because what does this problem look like to you? A little bit. What type of problem? Hess's law. Yeah, this is a Hess's law type problem, and this is where that stuff kind of comes in more handy. Problem. There we go. Hess's law type problem. So we want to add these 3 equations to look like that equation, right? All right. So remember, we can manipulate these. We can multiply them by 2, flip them over, all that sort of stuff. But we know the equilibrium constants for each one of those. We're trying to figure out the equilibrium constant for that reaction. We don't know the K for that, but we can use the K's for the steps and ultimately solve for the equilibrium constant for that reaction. Okay? So what do you guys want to do with the first equation here? Should we flip it, multiply? What should we do with it? Or nothing? Why do you guys say nothing? Why nothing, Josh? Right, yeah, I mean, 2 HBr, HBr is only present in that reaction, and it's on the product side there, so it's got to stay written as is. Okay, so I'm going to leave that one as is, and I'm going to rewrite it down here, though. So K1 is equal to 7.9 times 10 to 11. All right, what about the next one? What about reaction number 2? What should we do with that? Right? Flip it around, okay? Yeah, we can flip this one because we got to get that H on the right side. And hopefully this will help us eliminate the hydrogen there. So I'm going to call this K2 prime because we flipped it around, right? Because we flip it, we take the inverse of K2. So it would be 1 over K2 which is going to be 1 over 4.8 times 10 to the minus 11, which is what I put on that one. I got 2.1 times 10 to the 40th. Yeah. Oh, I'm sorry. It should be 41. I was looking at, I mixed those two together in my head there. Should be negative 41, right? There you go. Sorry about that. Oh, I wrote it as negative. Oh, I'm sorry. My bad. Thank you. There we go. Sorry about that. All right, what do you guys want to do with the last one? Flip it, okay? So we'll flip that one too. VR. I'm going to call this K prime number 3. So 1 over K3. I got, for that one, I got 4.5 times 10 to the 14, hopefully. So if we add these guys together, H2, VR2 cancel, then we're left with 2H plus 2VR. 2HBR, right? And I actually ended up getting, I got that K value when we multiply them all together. We take K1 times K2 prime times K3 prime. I ended up getting that. That's when it becomes valuable to you, like being able to manipulate the K values for a Hess's law type problem that you might see. Okay. And the last one's just really calculating K for the last one. Yep. You're multiplying. Yeah, you multiply them all. Hess's law, you add the values. Here, you're going to multiply. Yeah. For the Hess's law with the enthalpies, you'll add. For this one, you'll multiply. Yeah. Yeah, that's the kind of key change with that. Yeah. All right. So that's it for today. Okay. The bottom one is just calculating at equilibrium. You're calculating the equilibrium constant for each one, and you just got to show that they equal, that they're the same. Yeah.
But this one, it says it only asks for the expression. So what's the expression?
What is the equilibrium expression? Oh, it should say what's the equilibrium value for the reaction. If it was just asking for the expression, right, you would write, it would be, so the equilibrium expression is going to be products of reactants, so HBr squared over H squared Br squared. Like that would be the expression. Yeah. So expression is only the, like just the, what it looks like, right? Without any numbers or value or anything like that. Okay. Yeah. All right.